All right, moving on to the Ka. Now, a Ka is specifically an equilibrium constant for an acid reaction with water. Strong acids donate all of their hydrogen atoms. We'll assume 100% ionization occurs. This is what we call a strong electrolyte. So H3O plus, we can identify as the product of a strong acid. All right, the acid concentration, HA, can also be written as the H plus concentration. It can also be written as the H3O plus concentration. Where does that come from? A strong acid plus water will always give us H3O plus and A minus, the conjugate base. Acid, water here is acting as the base. We have our conjugate acid, H3O plus, and our conjugate base, A minus. Now for a strong acid, if this acid is strong, it will completely ionize with water to form the conjugate acid, H3O plus. So that's why there's that equating right there. Now, H3O plus can be reduced down to just H plus. I typically use H3O plus, but I'm going to use them interchangeably right now just to practice. All right. The other way that this is, or the other why we use H plus as well, is because we could simplify this equation and say that HA ionizes to H plus and A minus, right? That means the same thing, just assuming water is in the solution. Now, there are 6 strong acids that you need to know. The binary acids HCl, HBr, and HI are all very strong. The oxo acids, nitric acid, perchloric acid, and sulfuric acid are also important. You got to know these, all right? Their Ka, the Ka, again, the acid dissociation constant, products, H3O plus, A minus, over reactants. Water is a pure substance, so this does not get included in the Ka. There's your Ka, right? Ka for a strong acid would be very, very large, something greater than 1. Lots of products being formed. For weak acids, it's the opposite. The Ka is less than 1, all right? So the amount of weak acid in the solution is not equal to the amount of H3O plus. The amount of H3O plus is actually a lot smaller, right? Because we don't have a lot of products. So the weak acid does not equal the amount of H3O plus or H plus in the solution. We cannot just use the concentrations equatably. If we wanted to figure out the pH, or what we'll talk about in class, the amount of H3O plus at equilibrium, we'll have to use an ice table. All right, examples of our weak acids would be vinegar, acetic acid, carbonic acid, things like when you bubble carbon dioxide into soda and you make carbonated water, there's carbonic acid in there, and formic acid. Now, the strengths of the acid are going to be able to be looked at in terms of the equilibrium constant, the Ka. We will see a Kb for bases, all right? So we have our 2 reactions here. Again, the Ka is going to be H3O plus concentration times the conjugate base, or A minus concentration, over the original Ha. For the base, a Kb, when a base is added into water, we have the Hb and the hydroxide concentration over the original base concentration. All right, so the magnitude of these will be able to tell us the strength. All right. There again is the acid dissociation constant, so that you can see the Ka can be written in 2 different ways. They mean the exact same thing. The larger the Ka value, the stronger the acid. The larger the Kb value, the stronger the base. So be very aware of what that subscript is looking at. It will tell you which equilibrium reaction you're doing. Acid with water, Ka, base with water, Kb. Now we have a nice chart here to tell us what the common Kas are for a lot of our acids. We see them right here. Nice. Next to it is a pKa. I just want to highlight this. We'll talk more about the pKa a little bit later, but it is a much easier number to digest. Notice the difference here. The only difference between them is the Ka has large negative exponents, the times 10 to the 2s, negative 2s all the way down to times 10 to the negative 10s. And the pKa is a whole number, or is a number instead of a scientific notation. And it goes from about 2 to 10, and it's not negative. And so when we're looking at the pKa, the only difference between them is a slight calculation. pKa is the negative log of the Ka. So we're trying to digest that value a little bit better. Okay, we'll talk more about the pKa and what it means and how we use it. We'll talk about the Ka as well in class and be able to see these new types of equilibrium reactions being involved the same way as what we did in chapter 15.